This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 1 of Week 5. The Rankine steam power cycle, the backbone of every steam plant on the exam. 4 components, 4 enthalpies, and one number that matters: thermal efficiency. We trace the loop on a TS diagram, then run a full cycle from the steam tables. The Rankine cycle is the closed steam loop behind every steam plant. 4 devices, 4 processes. The boiler adds heat at constant pressure and makes high-pressure superheated steam. The turbine expands that steam isentropically and produces shaft work. The condenser rejects heat at constant pressure and turns the wet exhaust back to saturated liquid. The feed pump compresses that liquid back up to boiler pressure. Number the states 1 through 4 around the loop, and the whole cycle becomes reading 4 enthalpies and subtracting. Thermal efficiency is the fraction of boiler heat that leaves as net work. Net work over heat in, or equivalently 1 minus heat out over heat in. Every term is an enthalpy difference across one device. Boiler heat in is H3 minus H2. Turbine work is H3 minus H4. Condenser heat out is H4 minus H1. Pump work is H2 minus H1. Net work is turbine work minus pump work. The 2 efficiency forms are identical because energy in equals energy out around the loop. Pump work. You could read H2 from a compressed liquid table, but those are sparse. Instead, use the reversible flow work integral minus the integral of V dP. Liquid is nearly incompressible, so V is constant, and the integral collapses to Vf times the pressure rise. Then H2 equals H1 plus that term. Watch units. Specific volume in cubic meters per kilogram times pressure in kilopascals lands straight in kilojoules per kilogram. Pump work is usually under 1% of turbine work. Small, but the exam rewards carrying it. It is small because you are squeezing a liquid. The turbine works on a vapor with a far larger specific volume. The 4 states. State 1 is saturated liquid at the condenser pressure. Read HF and VF. State 2 is computed from the pump shortcut. State 3 is superheated vapor at the boiler pressure and temperature. Read enthalpy and entropy. State 4 is the turbine exit at the condenser pressure, where the isentropic constraint sets entropy 4 equal to entropy 3. That entropy lands inside the dome, so state 4 is wet steam with quality X4. States 1 and 3 are your lookups. 2 and 4 are computed from them. Worked problem. An ideal Rankine cycle makes steam at 8 megapascals and 480 degrees, exhausting to a 10 kilopascal condenser. Turbine and pump are isentropic. Here is the plant. The feed pump raises the pressure from state 1 to state 2. The boiler adds heat to make superheated steam at state 3. The turbine expands it to state 4 and delivers the shaft work. And the condenser rejects heat to return saturated liquid at state 1. On the temperature entropy diagram, that same loop becomes a rectangle pushed up into the superheat region. Boiler across the top, turbine straight down into the wet region, condenser along the bottom. Find the thermal efficiency and the turbine exit quality. The plan: states 1 and 3 straight from the tables, state 2 from the pump shortcut, state 4 from the isentropic constraint to get the quality. Then assemble heat in, net work, and efficiency with a cross-check. States 1, 2, 3. State 1 is saturated liquid at the condenser pressure, enthalpy HF, plus the entropy and the Fg terms we will need for the exit. State 3 is superheated steam at the boiler pressure and temperature. Read enthalpy and entropy directly. State 2 is the pump. Vf times the pressure rise gives about 8 kilojoules per kilogram. So H2 is H1 plus that, just under 200. State 4. The ideal turbine is isentropic, so entropy 4 equals entropy 3, carried to the condenser pressure. That value sits between SF and SG, so the exit is wet. Quality is entropy 4 minus SF over SFG, about 0.80. Reuse that same quality with the enthalpy terms, and H4 is about 2100. Turbine work is now locked in, H3 minus H4, about 1240 kilojoules per kilogram. Assemble. Heat in is H3 minus H2, about 3150. Turbine work, 1240. Pump work, 8. so network about 1232. Efficiency is network over heat in, 0.391. Cross-check the loss form. 1 minus heat out over heat in gives the same 39.1%. Both routes agree. Efficiency about 39%. Exit quality about 0.80. Raising efficiency. Our exit quality came out around 0.80, below the roughly 0.88 limit where droplets erode turbine blades. Real plans fix that two ways, both of which also raise efficiency. Superheat raises the inlet temperature, adding heat hotter and drying the exhaust. Reheat expands partway, sends the steam back to the boiler, then finishes the expansion, keeping exit quality high. The lever behind all of it is the average temperature of heat addition. Raise it, and efficiency climbs, because Carnot sets the ceiling. 4 traps. 1. Get exit quality from entropy, not enthalpy. Entropy is the isentropic bridge, then reuse that quality for enthalpy. 2. Don't drop pump work when the data demands it. VF times the pressure rise, units in kilojoules per kilogram. 3. Read state 3 off the boiler pressure superheated table and states 1 and 4 off the condenser pressure table. Mixing pages cascades. 4. Respect the condenser loss. It is why efficiency caps near 40%, and the 1- form is there to catch a drop term. Bookmark the cycle pages. The Rankine efficiency in enthalpy form. The heat engine form, 1- heat out over heat in, with Carnot as the ceiling. Turbine work, H3 minus H4. The pump shortcut, VF times the pressure rise. And the 2 steam table pages that do most of the work. Saturated by pressure for the condenser end, superheated for the boiler end. Fold both corners. You now own the bones of the steam plant. 4 states, 4 enthalpies, 1 efficiency. Today's ideal cycle hit about 39% with a wet exhaust near 0.80. In topic 2, we add the upgrades real plants use, reheat to keep the turbine dry, and regenerative feed water heating to recapture energy headed for the condenser. Same 4-state skeleton, more states bolted on.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.